Hello everyone. Today we're going to be talking about lesson 8, which is hydrolysis. This is a really interesting lesson. I just wanted to tack it on to the end here because it is a really exciting subject, and it kind of ties a bunch of ideas together. So when we consider the idea of weak acids and weak bases, one of the statements we said at an earlier point was that the conjugate acid of a weak base was a strong acid, and the conjugate base of a weak acid was a strong base. Well, this has implications. That means that if you create a situation where you have a weak acid or a weak base, when they dissociate, the other chemical that it produces is going to be the opposite type. It'll be either acidic or it'll be basic. And so this has some effects. So if you mix two strong acids together, a strong acid, strong base, and you neutralize them, well, that's fine. Because the conjugate base of a strong acid is a weak base. The conjugate acid of a strong base is a weak acid. So this essentially means that on the opposite side, we're going to have a weak acid and a weak base. But if you try to do this chemical reaction with a weak acid and a strong base, well, now you're going to have a strong base and a weak acid. So you tried to go and neutralize some weak acid, and the result is that you don't end up with the neutralization you expect. You end up with a basic neutralization. So even though you used exactly the same amount of acid and base concentrations, the result is that the pH is actually a little bit higher than 7. Do this again with a strong acid and a weak base. Then you can also have a similar problem where the strong acid creates a weak base, but the weak base produces a strong acid. So when you create this situation where you used exactly the same amount of acid and exactly the same amount of base in terms of moles, the result is that you are going to have, due to the products of that reaction, you're actually going to have a solution that's not neutral, but it is actually a little bit acidic. So the only time this is going to work out is when a neutral salt, the neutral salt that's formed is the salt of a strong acid and a strong base. Those salts, they will all be highly soluble, and they'll have very little interaction with water, so they won't affect the Kw. They won't affect the hydroxide hydronium interaction. So the following anions of strong acids do not affect the pH of solutions. Those include chlorides, perchlorates, iodine, bromides, and nitrates. Also, any group 1 or 2 ion will not affect the pH of a solution. So these are all of our highly soluble, right? These are our high solubilities. So that's really the key, is solubility. That's why we did that solubility unit first. Now, if you choose any of the other ones, then you might have some problems. So acidic salts are due to the formation of conjugate acid of a weak base. For example, ammonium nitrate is the salt formed from the reaction of ammonia with nitric acid. In water, ammonium nitrate dissolves to form ammonium ions and nitric acid. But this ammonium ion, NH4, is actually a conjugate acid of NH3, and it's a fairly okay acid. It's not the weakest acid in the world. And so now you have an acidic chemical that you created. So so we have to keep track of these sorts of things. Now, basic salts, for example, so sodium acetate is an example. In the case of sodium acetate, if you dissolve some sodium acetate, it dissolves into sodium and acetate, but then this acetate has the ability to react with water to form acetic acid and hydroxide, so at which it can form a basic solution. So here's the type of example we can do here. So is potassium carbonate an acidic or basic or neutral? Well, we think about potassium carbonate, it is highly soluble, so it will dissolve, and we are going to get some 2K plus ions, which are sort of our spectators here. And we'll have a reaction with water where we form HCO3, which is one of the carbonate ions, one of the products of carbonic acid. And so this has resulted in the formation of hydroxides, and so hydroxides form from this reaction with water, so the solution is basic. Now, in the next question, they mentioned something called a Lewis acid, and I just thought we'd throw this in there just to, we haven't done enough crazy stuff yet. So a Lewis acid is a particular type of acid where it accepts electrons from it's an electron acceptor. So it's just a rejiggering of our definition of acid. So an acid could be a proton donor. An acid could increase the hydronium concentration. But an acid could also be an electron acceptor versus a Lewis base, which is an electron donor or electron pair donor. Particularly, we were interested in what's called a dative bond, but I'm not going to get into that. That's too much work. So a good example of this is many of the boron compounds. So this is boric acid, BOH3. And you might look at boric acid and say, well, this has 3 hydroxide groups on it. How can it be an acid? Well, it's an acid because it can accept an electron pair from a hydroxide to form BOH4. Well, if we put this into context with let's put this into context with a reaction with water, what we're actually talking about is that this is going to form BOH4 minus, and H plus is the result. So it is an acid, right, because it has increased the amount of hydrogen ions in solution, and it has also removed the hydroxide from the solution. So that's also another way of being an acid. So that's an example of a Lewis acid. There are a couple other examples. NH3, for example, often works as a Lewis base. So it has an electron pair here. And then when it reacts even with water, for example, what we're reacting with here in water is this electron pair is attacking the Lewis acid of the hydrogen to make a NH3 like this, or NH4 plus, and it produces a hydroxide. So that's another example where we have a Lewis base reaction. So it's our Lewis base. Okay, so plug that in somewhere in your mind. It is a definition that definitely becomes more useful as you go on into university chemistry. It's not something I will test you on now because we don't have a full lesson on this definition, and it's not included in our curriculum. But I just want to bring it up as another example of this type of reaction. So it's important to list salts containing 3+ or 2+ metal ions, except for the group 2 metals, will be acidic in water. And we learned earlier that these metal ions are considered Lewis acid response to. So for example, iron chloride is acidic in water because the iron ions are an acid with a Ka of about 10 to the -3. And so here's the example. Here's iron. It's dissolved in water with 6 waters around it. But when it reacts with water here, with loose water, you can form a H3O because the iron will gain a hydroxide. And so here's the hydroxide floating in it, attached to it. And that's attached through one of these Lewis acid reactions. Oxides are basic in water because an oxide can accept the hydrogen in water to form a hydroxide. So let's look at some examples. Here we have sodium sulfide, so NaS or Na2S. Think about what is it going to do when it reacts with water. Well, when it reacts with water, we are going to see the formation of essentially The sulfide is soluble, so it separates out. It can be treated as being sodium plus and sulfur 2 minus. And then thinking about how that would interact with the water, we can have H2S form and essentially sodium hydroxide, right? This sort of reaction. And yeah, we do need to. Okay. And so that produces hydroxide, so this is a basic solution. Okay, so for potassium acetate, we have KC2H3O2, and that dissolves in water. And so when it dissolves in water, we're going to get K plus C2H3O minus. And then that C2H3O minus plus a water would result in the formation of acetic acid plus an OH group. And we know that acetic acid is a weak acid, so that equilibrium is going to complete itself, and we're going to be talking about the Kb value for that acetic acid. Okay, chromium bromide. We know that bromide is not a danger because that's part of a strong acid, hydrogen bromide, and or bromic acid. But the chromium 3 will attract hydroxides in solution, and so we would be looking at something like chromium 3 plus, which has some amount of waters around it. I don't know how many. Let's put 6 for sure. Plus an H2O, and the result will be that the chromium, the dissolved chromium, and we should probably put this on the opposite side here. Get over there. Okay, there and there. Okay, so the result is going to be that at least one chromium hydroxide is gonna join up. Now, I mean, I'm just making some guesses here as to how many waters it has. Chromium is a little bit of a smaller element, so probably 6 is a pretty good bet. And the result is an H+. So this is an acidic solution. And this one was basic. Okay, potassium dihydrogen phosphate. So we are talking about KH2PO4. So that's an interesting one. H3PO4, just put this on the side note here. H3PO4 is a strong acid, right? So this is a strong acid, so it goes straight to HPO4. But H2PO4 is definitely not going to be able to reverse that, right? So we're not going to be able to go back to that H3PO4 even if you put a water here. So in fact, the H2PO4 is going to have a little bit of an equilibrium, and it's going to be able to donate one of those hydrogens to make HPO4 minus plus H3O plus. So in that way, it is an acid. So this dihydrogen phosphate after the first proton that comes off of phosphoric acid, so it still has another proton that it can lose. For the next one, we have sodium nitrite. So this is NaNO2. And this compound is, what we want to do is an extremely strong acid. So the reaction would be entirely backwards. So, let's play the game out a little bit. HNO3. And so the reaction would be only to go this way. It would be very, very strong acid. This would also be a strong base, right? So strong acid, strong base. And so we can think about this as having no reaction. Okay, so hopefully that makes a little bit of sense, and you can play around with the practice questions that follow. I think it's a very interesting unit. It's very close to a concept called buffers, which is incredibly important if you want to study that really plays on this idea that we have a second part to our acid components. They aren't just the H+. There is this salt part, and playing around with those salts gives us a lot of different products and different ways of controlling the hydrogen and the hydronium and the hydroxide concentration. Hope you enjoyed, and we will talk to you soon about the next subject.